Good afternoon, everyone again. So again, we will do review session today for exam 1. And exam will be in class Lehman 267 and Lehman 269. Okay? Second floor 267 and 269. Does anyone has a class before this one? Right before? Okay. What about, does anyone have a class right after? Okay. So we can start at 12:30. I'm just trying to give you an extra time. Okay. We can start at 12:45. 12:35. That works. Let's see. That works for Zoom people. Okay, I guess it works. Okay, 12:35. But again, if you come early, you can come, right? I will be there early as possible is better. Usually students need more time. Okay. Unfortunately, there's a class right after us in that room, both of them. So we have to leave before 12:10 or 2:10. Okay? I will not be providing anything except problem. Tables, calculators. You will bring your own. Okay? Okay. Let me know if you have any questions. Exam number 1, review. Okay. Concept and definitions. I don't usually ask concepts and definitions or unit conversions or what is this, how do we use it? But every problem has those, okay? So do not underestimate those. If you don't know the definitions, I will highly recommend that go back and read it. Okay? Properties. States and processes. Conservation of energy. Right? First law of thermal for closed systems. And then we define the work, the expansion form, and compression or contraction work. And we also define how to find work, right? Pure substance. And their first law applications. Ideal gases and their first law applications. This is basically all of the titles we've covered so far, okay? And basically it's from chapter 1 to 3, right? First 3 chapters are book. Okay. Thermodynamic properties. Intensive properties. Temperature and pressure. Bar or kilopascal. Celsius, Kelvin, Fahrenheit, degree Rankine, etc. Extensive properties. Volume. Internal energy. Meter cubed. Kilojoules per kilogram. Enthalpy. Kilojoules. Okay. And we also had specific properties, which are derived from extensive properties, right? Extensive properties per mass called specific properties. Specific properties. Specific volume. Meter cubed per kilogram. Specific internal energy. Kilojoules per kilogram. Specific enthalpy. Kilojoules per kilogram. Thermodynamic processes. Through heat and work, or upper letter W. Heat is the energy transfer due to a temperature difference between the system and surroundings. Work is also energy transfer due to a potential difference other than temperature. Either it is done by a system that's the case if the sole effect external to the system could have been the raising of a weight. First law of thermodynamics for closed systems. Stored energy difference between two states would equal the heat transfer minus the work interaction occurred during process. And stored energy is internal energy, right, plus kinetic energy, plus potential energy, magnetic field, etc. We have many others. By neglecting kinetic and potential energies, what we have, internal energy difference from state 1 to state 2 equal the heat transfer from state 1 to state 2 minus work interaction from state 1 to state 2. Expansion and compression work. Again, we are still talking about closed systems. Everything we are talking about is based on the system closed. Closed system to the substance and compress it or expanding the volume. I have creating a work, right, applied on the system or applied by the system. The difference is sign convention, and you should be careful with that, right? Same with the heat and other properties. Okay, and we know how to calculate work, right? Work equals integration of E dV. Okay. Work from state 1 to state 2 dV. And we have couple processes, right? Isometric, isobaric, isothermal, adiabatic. And subtitle of these, we have also linear processes, polytropic processes, and etc. for each. For polytropic process, if n is bigger than 1, we said that work is P2, P2 minus P1, P1, divided by 1 minus n. If n equals 1, work equals PV natural log of, if it is a state 1, P1, V1, natural log of V2 over V1. For P2, V2, natural log of V2, V1. State postulate for simple system only two independent properties are needed to completely define the state of a simple system in thermodynamics. Temperature and pressure, for example. Temperature and specific volume. Specific volume and pressure, etc. Pure substance. In this class, we will mostly dealing with water, refrigerant 22, refrigerant 134A, ammonia, propane, etc. Okay, there are other refrigerants available outside. As long as you know how to treat these, you should be able to handle those as well. And when it comes to properties, we had a couple ways to find them, right? But we go with tables. We use tables to relate properties such as temperature, pressure, specific volume, internal energy, enthalpy, entropy, etc. pressure, volume. We call this A, B, C, D, E. A is compressed liquid. Compressed liquid. And B, saturated liquid. C, wet vapor. E, saturated vapor. E, super heated vapor. Also had a critical point on top of the dome. If we have a wet vapor, right, we had an additional property we call the quality factor. Quality of the substance. Let me show it with X. X, mass fraction, gas, the total mass. So X can be found as specific volume minus specific volume of saturated liquid minus saturated specific volume of saturated vapor minus specific volume saturated liquid. Or we have internal energy U minus UF over UG minus F. If you know enthalpy, H minus HF over HT minus HI. After pure substances, we started also another pure substance, which is ideal gases. And the reason they call ideal gases is they don't change phase. Okay? The substance that exists only in vapor form from its saturation zone when it is under normal operating conditions. Which are air, carbon monoxide, carbon dioxide, nitrogen, hydrogen, oxygen. And P V equals RT. R equals universal gas constant over a molecular weight. T times V equals RT for T, V, MRT. For P, V, and RUT. For ideal gases, internal energy difference from state 1 to state 2 equals integration CVDT. Enthalpy, specific heat at a constant pressure T, and they both have two cases. Right? Specific heat or variable specific heat constant. Right? Q minus T1, T2 minus T1. Tp, T2 minus T1, or H2, HT2 minus HT1. R equals Cp minus Cv, and ideal gas ratio K equals Cp over Cv. This is basically what we have covered so far. Okay, so we have everything for the exam. Yes.
Can you scroll the page number 6 down a little bit, please?
Okay. In class exam, Lehman 267 and 269. From 12:35 p.m. to 2, 5, 10, we will decide on that, okay? Let's see how it goes. Let's say 2 now, for now. If you need extension, extra time, I can give you maximum 10 more minutes. Okay? There's another class taken that room, starting at 2:15. Okay? Yeah.
So if we did time before class, we come 10 minutes earlier than that as well, and 12:35. Let's say we had a class.
10 minutes.
Mhm.
You can even come earlier, 5 minutes, then 12:30, you didn't accept it.
Okay.
You said it's too early. It works for me. Yes.
What about if you run a couple minutes late, because I have a class that ends at 12:30?
It's okay. Okay. Please bring your calculator and tables. If you don't like printout tables, you can bring a PDF format. Okay? That works for me. Any questions? Yes,
How many questions do you have?
I haven't decided yet, but usually I ask 2 or 3 questions.
So they're all gonna be kind of like the homework style questions,
Homework style meaning
like, as in. it's-
homework questions are easy and short.
Yeah.
They are practice purposes. Okay? But in the exam, try to measure your knowledge. If you know it, right? Or not. If you can apply it. Homework problems are heartless level, I would say 6, 7 out of 10. But exam will be 8, 9. Okay? This is exam.
I just want to know, like, the exam, is it just to answer one thing, or is each question?
Same thing. It is pretty much what we have done in class. Sketch the PV diagram. Show this, find this. Right? A, B, C, D. Multiple choices, but you need to know what is A in order to solve B. Okay. So nothing different. Anything else?
Or bring some paper to work on?
You can. I can also provide that. You can bring your book, you can bring your notes.
So that we can get it.
You can. Sure. Okay. I think that's all. So an example problem. Yes.
I have all my notes on a tablet.
Sure, you can bring your tablet. Yeah, you can use it. Example. It will be page 8. Gas is contained in a vertical piston cylinder assembly by a piston with a face area of 40-inch square. weight of 100 pounds. The atmosphere exerts a pressure of 14.7 pound force per inch squared on top of the piston. The pedal wheel transfers 3 BTU of energy to the gas during a process in which the elevation of the piston increases by 1 feet. Negligible friction and Q is 0.
Is it?
What? Yes.
Is that 1 foot or 9 feet?
1. Okay. It's not a SI units, as you can tell, right? But everything is same rules. First off, thermodynamics, everything is same. Okay. We will be using tables again for relating properties. You have US customer units tables available on Canvas too. Okay. Sometimes I ask US customer units as well, but it's just the same thing. Yes.
Would you like us to have the SI unit tables and the US customary tables? If you can?
Cool. Okay. We have a piston cylinder assembly, okay, which is a closed system. Basically, we can apply everything we have covered so far on this problem. And closed system, gas is contained. Only difference is CS customer units. State 1 and state 2 piston increases 1 feet. One feet. Has also pedal wheel inside the system. Yes. Piston area is given. A piston equals 40 inch squared. And weight of the piston is 100 pounds. After a process, I end up with this. But what is the process here?
Expansion.
Yes, but expansion is not a process.
Isobaric.
Isobaric, isothermal, isometric, adiabatic, adiabatic. Yes. What else? To me, this problem is similar to what you have solved in assignment. Okay. To answer your question. Yes, well, isobaric question, isobaric process, right? Why? Surrounding pressure doesn't change. Whatever the pressure I have in the beginning, I carry that pressure along the process. Okay. As I mentioned in the previous lectures, it will not be stated clearly in the problem statement that what kind of process you are dealing with. That is the case most of the time. You need to know how nature behaves and treat that problem accordingly. Okay. In this case, it's a isobaric process. Laws are that. Okay. State 1. And state 2. Process, constant pressure, and work on pedal wheel is 3 BTU. But it's minus. Okay. We already assumed that it's adiabatic. Right? Kinetic energies and potential energies are negligible. Frictionless. And it's a closed system. From a first law of thermodynamics, stored energy difference equals Q minus W. That equation, Q is 0. Right? And stored energy as a kinetic energy and potential energy terms, they're 0, right? Or negligible 0. All I have left is internal energy difference from state 1 to state 2 equals work. Right? But it's a minus work. You gotta be careful with the sign conventions. And this work has two terms. Pedal wheel and the work from an expansion. Expansion. This is given, and I can calculate. How? PdV. Good. Work. Mention. State 1 to state 2. PdV. What is my P?
14.7.
14.7.
I was still waiting for this.
Good. I thought you have taken physics. What happened to fatal piston? We have a way, the area, which we can calculate the force of it. It creates additional pressure in the system. Okay? Plus atmospheric pressure. Okay. Volume, let's call this pressure of the gas, area, and the elevation. Okay. From state 1 to state 2. Okay. This is volume, right? Area times distance. AB is area, C is volume. dx and dx. Right? Okay. My piston has a couple forces on it. Has atmospheric force, which is atmospheric pressure times area. And we have also weight of piston, 100 force. And the positive y direction we have gas times the area of the piston. Now I can do something. P gas, right, H times A piston, this term. If I call this Fy, it should be 0. It should cancel out. Gas, P gas times A piston minus P atmosphere times F piston equals weight of the piston. P gas, right? That's all I care about. Pressure inside the chamber. What is being applied to the gas. So I can calculate my work. And P gas, if I take it on the, or if I leave it on the left hand side, right? P gas will be equal to P pressure atmosphere plus weight of the piston divided by area of the piston. Atmospheric pressure is given as 14.7 pound force per E squared plus weight of the piston over the area is 40 inch squared. Should give you 17.2 pound force per square. And we said work expansion equals P gas times piston times Px from state 1 to state 2. I know my P gas, I know my area, I know my X. So I can find my work expansion. P gas times area of the piston times x2 minus x1. Work expansion from here, we have P gas is 17.2 for steam squared times area 40 inch squared x2 minus x1 is 1p. But this will not give me the unit that I want. I need BTU. And if you want to convert this to BTU, 1 BTU equals 778 P times pound force. Work expansion from here will be 0.88 BTU. You can double check my answers. So energy stored in the system can be found from first law of thermodynamics now. Right? From state 1 to state 2, the energy stored in the system is that Q is 0. It's only equal to a work interaction in the system. I know my work introduced in the system through paddle wheels, and I know my expansion. Right? So I can find my stored energy in the system. Delta U will be equal to minus work. And that work, paddle wheel plus expansion. .12. Delta U will be equal to 2.12 BT.
Why would it be 3.88?
Because work pedal wheel is minus 3.
Okay.
We have 4 terms. Q in, Q out, work in, work out. Q in positive, Q out negative, work in negative, work out positive. Okay, and you have a plus negative sign in the equation. So you got to be careful with the sign convention. That's a usual common mistake. If you haven't started studying, I recommend you to start. So it's a 2.12 BTU. We didn't need any properties from the table, but if you needed, you could have. Right? You go to US customer unit tables. They're read in the same manner as the SI units. And make sure you know how to read tables. Linear interpolation, linear extrapolation. Make sure you practice those. Okay. So we have 10 minutes left. I don't think we can solve problems, but I can answer your questions.